Okay, now I just wanted to go over an example, and again, this is in chapter 9 right here. We're looking at rotational energy right here. And remember, we brought up the moment of inertia I, and I for a stick, at least in the book, about the center of mass is given by 1/12 m times the length of it squared. If we pick one point on the edge of the stick, that's 1/3 ml squared right here. It's got more rotational inertia rotating about the end than it does about the middle right here. So suppose we have a stick that's pulled out 90 degrees and we just let it go and let it just fall down right here. And what I want to calculate is what is the angular speed that this thing is moving when it gets to the very bottom, and then what is the speed of just the tip of the stick right here. So I'm going to say it starts from rest, and you're given the length of the stick right here. We want to find the omega when it got to the bottom and the speed at the very tip when it's at the bottom right here. Well, since we're rotating at about one end, our I is given by 1/3 ml squared right here. Now, since we're using energy, this thing starts out with potential energy. Now, remember, potential energy is mgh right here. Now, one way you could look at it is you could say, well, this little piece started way up here. He was a total height of L. He dropped a total length of L. But this piece only dropped to here, less than L. And this piece right here barely dropped at all. How do we handle the potential energy since they all went down different amounts right here? Well, luckily, we can assume all of the mass is at the center of mass for potential energy. So again, all the mass we can assume is right there in the middle of the stick, and there it is at the middle of the stick. You can do this for potential energy because potential energy goes as mgl to the 1 power. If it was squared, you wouldn't be able to do this. Okay, so when we look at potential energy, I only have to look at these 2 points right there. Now, if I call this height 0, then the potential energy when we're vertical like this is just mg times, what's that, L over 2. And when I'm way up at the top, the potential energy would be mg times L. That height is L. Okay, so we can say the initial energy, when you're way up there, is just mgl. That's the total height. The final energy right here is, well, you've got the mgl over 2. You got the potential energy for the center of mass, plus it's rotating. And it's all rotating about this point. This point isn't moving. If this point were also moving, then you'd also have to add a 1/2 m velocity of that point squared. But that point is fixed. So all we have is the rotating about that point and the potential energy right here. Again, I said use center of mass for the potential energy. That's big right here. Okay. So all we have to do is set these two equal. There is no energy loss right here. So we have mgl, here's the initial energy, equals 1/2, and then the I we said was 1/3 ml squared, omega plus mgl over 2. I'll bring this term over to this side, which gives me mgl over 2. Combine this, that's 1/6 ml squared, omega squared. We'll cancel a 2, cancel an m, cancel an l, and then take the square root of both sides. And so omega at the bottom is the square root of 3g over l. And then if we wanted to get the speed, v equals r omega, r is l. So once we know omega, we can get the speed right here. And in this case, it's L omega, which is the square root of 3GL right here. Okay, I just wanted to remind you, we did this for just a little pendulum pulled up and let it go, a little point mass, and it was the square root of 2GL at the bottom. This one's actually going faster right here. So if you race this against just a little pendulum swinging down, this would beat it right here. Okay, now let's look at one that's a little more involved right here. Here we have another disk right here. It has a mass of 4m and a radius of 2r. So that means it's I, since I for a disk is 1/2 mr squared, it's 1/2 4m 2r squared. This is just another disk, but his mass is 2m, and his radius is just r. So there's his 2m r squared. Okay, so we have this mass right here and here. This one's heavy enough. This is going to start rolling down this way as this goes up. And at some later time, this disk has gotten down to here. This has moved up to here. This distance is the same as that because they're tied together right here. Now, the system starts from rest, so there's no initial kinetic energy. And I also said no slipping on any surface. So what does that mean? That means, first of all, it means the work due to friction is 0 because you only have work loss if there is slipping right here. Also, that the speed that this object moves is the same as the speed of the rope, which is the same as the speed of this surface right here. Which means that the omega of this surface is just the velocity of the surface, which is the same as the velocity of these blocks, divided by r. This one over here is rolling without slipping, so his omega is the velocity of the rim is the same as the velocity of the object, right here, because it doesn't slip. So we can say omega of this guy, the rate of omega, is the velocity over 2r right here. So you have one similar to this on your homework right here. Okay, so now, first of all, we're starting out like this. And I'm going to call h equals 0 here for this block and here for this block. And so the only thing that has energy, there's no kinetic. All we have is this one has some potential, h sine theta. And its mass is 4m. So the initial energy is 4mgh sine theta. Okay, now this thing's going to start rolling down. He's not going to lose any due to friction, so the energy here is going to be the same right here. Well, where did all this potential go into? Well, first of all, it went into lifting this up. So some of it went into mgh right there. And then the rest of it went into, this one's moving, this is turning, and this one's turning and moving right here. So it went into all the kinetics, the kinetic of this guy, and the kinetic of that one, and the kinetic of that one right there. Okay, so let's just look at the kinetic of each one. The kinetic energy of this block is just 1/2 mv squared. He's not turning. Only translational motion. This one is only turning. He's not going anywhere. So it's all 1/2 I of the 2m omega squared. There was my I of the 2m right here. And we have omega, which is v over r, v squared over r squared. You notice the r squareds are going to cancel. They're always going to cancel. And this only has rotation. Again, no slipping right here. And then this one over here has got both. It's rolling. It's actually moving and turning. And so right here, we've got, this is the movement, and this is the rotation of, and this is the 4m right here. So we just plug in our I, 1/2 4m 2r quantity squared, times our omega squared, which is v squared over 2r quantity squared. The 2r's are always going to cancel. So you get both motions right here. So now I can just go ahead and plug all my kinetics up into here. And we have my 4mgh sine theta equals mgh plus all of the kinetics. Well, if we add up all three of these, we got a 1/2 mv squared here. We've got another 1/2 mv squared here. We have another one, these two 2's drop out and the r's drop out. We got another 1/2 mv squared there. And then this last one, we get the 2r's drop out, and we get the 4 over the 4's drop out, and you just get mv squared. So I can combine all of these terms together. A half, a half, a half, and 1 is 5/2 mv squared. Cancel an m, bring the gh on the other side, and so we get 4gh sine theta minus gh equals 5/2 v squared, or V, take the 2/5 on the other side and take the square root. There is the velocity right there. In the next chapter, we'll show you how you can do this all with forces, but we need to be able to handle the rotational forces right here. Okay, so this is how we're going to solve these problems. We can work them out either way, with forces or with energy.